first talk about span. So given vectors u1, u2, un, span of u1, u2, un is defined as the set of all possible linear combinations of this set. So it's like linear combination means there's some constant c1 multiplies the first vector, another constant multiplies the second vector, and another constant multiplies the last vector. Whereas c1, c2, cn belongs to the set of scalars. So I'll just put R for now, but this could also be possible as C. Okay. So that if you build a vector space on set of real numbers, you say it's a vector space over the ground field R. That's how people say it technically. Or you also say the vector space is a real vector space. That's how they say it. If you take C as the ground field, or if you say a vector space over C, then you call that a complex vector space. We'll eventually have to talk about the complex vector space, but let's make things simpler and just talk about the real ones for now. Okay? So I have this definition, but what does it mean? Let's think about what it means. So let's think about some very simple ones. So, example. Let's say you have u1 as the vector 1, 0, -1, and u2 as vector 0, 1, 2. Find the span of u1, u2. Okay. And then this is something that's a bit more challenging. I'll still write it. What shape is it? And equation for that. Let's think about that. All right, so span of these two vectors, 1, 0, -1, 0, 1, 2. Some of you may not be so accustomed to the set theoretical notation. This is a set theoretical notation, which means you're collecting everything that looks like this as a set with the conditions given here. Okay? So let's see what that means in here. It means that it's like some number times 1, 0, -1 plus another number times 0, 1, 2, where A and B are some real numbers. That's what it means. But let's further calculate this to see what it's trying to say. So this is trying to say you have A, 0, -A plus 0, B, 2B, where A, B are some real numbers. I guess you know what I mean by R with the extra bar on the left, right? Set of real numbers. What are real numbers? 1, 2, 3, 4, 0, -1, also decimals, radical 2, pi, all the numbers you can think of. What's a non-real number? Yeah.
Root of -1?
Yeah, root of -1, pi. So, because we're just talking about real vector space, we're just going to limit A and B to the real numbers. Okay, so what is this? This is like you have A, B comma, negative A plus 2B. Okay, what's the shape of this in 3D? Can somebody tell me? What kind of shape would this be?
Is it like a tube?
It's what, tube?
I said a tube. I know there's part of it is a line, but
Well, it's, okay. So let's think about this. You have x, y, and z.
it's not a tube.
1, 0, negative 1 would be 1, 0, and negative 1 here. So it's like this vector. So that's the first vector, 1, 0, negative 1. It's on the xz plane. It's going that way. And b would be 0, 1, 1, and then 2. So it's on, the second vector is somewhere here. It's longer. Okay. Now, because a and b could be arbitrary numbers, this span is going to contain these two vectors themselves, because you can choose 1, 0, and 0, 1. If you choose 1, 0, you get the first vector. If you choose 0, 1, you get the second vector. Or you can also just take b as 0, but a can be arbitrary multiple of this vector. What that means is that you have this entire line of points, and every point in here is some multiple of this vector, so it's included in this span. Is that okay? Yeah. Same thing with here. If you set a as 0 and b as any multiple, 1, 2, 3, or 0.5 or whatever, then it gives you all the multiples of this vector, so you get everything in this line. Right? But then, what if I have 1 and 1? What does that give you? You have two vectors, and if you have vector A, the first vector plus second vector, what does that give you? You get a third vector given by what rule?
Parallelogram rule?
Parallelogram rule. So there's this, it's hard to draw, but there's a parallelogram here where I'm drawing it like a 2D, but it's really sticking out. And it gives you this third point, right? And also, every multiple of that point will be included in the span as well, right? But then what if you have like twice of this plus 1, then twice of this is like here, and then this plus this gives you another point here. So you kind of see that you have all the possible vectors you can generate out of taking these two vectors. So what would you get eventually? A plane. You're going to get an entire plane that contains these two vectors. Okay. So the answer is the shape is a plane passing through the origin, okay, through 0, 0, right, containing the two vectors. Right? So you have a plane that's cutting through the origin that's passing through these 2 points. So it's like that. Right? That is a plane. Okay. But then, what's the equation of a plane? So plane in 3D. Do you remember how the plane in 3D looks like? What's the equation of a plane in 3D? It's been a while. So something x plus something y plus something z equals to another number. That's a plane in 3D, right? And moreover, if this is 0, then 0, 0, 0 is a solution. So it's a plane that passes through the origin, which is our case, right? So I know that the equation of a plane must look like this. And there are actually 2 ways to go about this. So this will be like a review in Calc 3. To get a plane equation, if you take these coefficients, you get a vector. What kind of vector is it? It has a name. It's called Has it been like 2 years?
Can you repeat the question, sorry?
If you have a plane in 3D and you take these coefficients, you can build a vector. That vector has a geometrical meaning with respect to this plane. It's called a
3D vector?
huh?
Would it be a 3D vector?
No. Oh, it is a 3D vector, but it has a name with respect to this plane. Okay, it's called a normal vector. Yeah. So normal vector is this, okay? Because if you actually drew the plane and this vector, they're normal, they're perpendicular to each other. The reason for that is because if you call this alpha, beta, gamma, and if you think of alpha, beta, gamma as a vector, dotted with this x, y, z vector,
Equals 0, yes.
is equal to 0. What does that mean? If dot product is 0, then the two vectors are
Normal.
orthogonal, right? It's normal. Normal means you have a direction that's perpendicular to a given
I thought
surface.
you were asking like what's the name of that specific.
Yeah.
I understand.
So that's a normal vector. Okay, good. So I have two vectors that's embedded in the plane, but I need the normal vector. How do you get the normal vector given two vectors? You do, it's all Calc 3, you do the
Dot product and then
cross product. Yes, if you do cross product, then you get the normal vector, right? So what you could have done was you can take I, j, k, 1, 0, negative 1, 0, 1, 2, and this gives you the cross product, right? So I times the determinant of this, which is 1i. The checkerboard of signs says I should put a minus for the j, and then it's a determinant of this, this, so it's 2, so it's minus 2j. And if I take k, it's a determinant of this one, that's a determinant 1. Right? So I know that the equation for this span, this has the equation 1x minus 2y plus z equals to 0. Okay? So that is the equation of this plane. Okay? This will give you a plane which is same as the plane described by this single equation. So that's one way to do it. Here's another way to do it. Say x is a and y is b and z is negative a plus 2b. Isn't that right? Where a and b are just arbitrary numbers. But then if x is a and b is y, then z would be what? Z would be negative x plus 2y. Because a is x and b is y, right? Well, wait, what is this? If you move everything to the left, what do you get? You get exactly the same thing, right? Right. So it's quicker that way. Yeah. So either way, you get the equation. Is that good? All right. So we get the equation that way. Okay, so hopefully you kind of understood now what the span is doing. If you're given multiple vectors, what does it do? It builds the entire space that contains the vector. Okay? So a way to say this is to understand this more abstractly. I have to talk about subspaces.
I have a question.
Yes.
So when we're doing the parallelogram rule, I know in statics that would be like, we're doing that to get the resultant vector. So then, would there ever be an instance where we would want to use a span for like...
Span is not just the sum of the two vectors, it's like all the multiples. So it creates the entire vector space that contains the two.
Creates that plane.
Creates that plane, yeah. But what I'm trying to point out is that if you have that plane, if you collect all the vectors that's inside that plane, that itself is a vector space. Because, see, here's an idea. If you have a plane that's going through the origin, and if you take any 2 points in the plane and make vectors out of them, right, then the sum of those two vectors still lie in this plane. Right? So vector addition is defined, and any multiple of a vector, you can elongate or shrink it or multiply negatives so to make it
go the opposite way, it again is in the plane, right? So scalar multiplication and vector additions are defined, and because they come from the bigger space, all the properties of the additions and multiplication that we require, the 8 properties, will still hold. Right? So this subset will be actually a vector space. So let me define another concept here. If U is a subset of V, this symbol here means a subset, and V and U is also a vector space, we say U is a subspace of V. Let me write down the criteria for subspaces. So if you are given a set and if you want to show that that's a subspace, you just have to show 2 things. Okay? So number 1, you have to show that it's closed under addition. And then number 2, it's closed under scalar multiplication. So in other words, if you have a subset, and if you take any 2 elements from the set, the sum is still in the same set U. So closed under addition means that for any UV in this subset U, U plus V is again in U. It's this pitchfork looking thing that's included in, okay? Or an element of. So if you pick any 2 elements, add them, and if that's still inside the same subset, we say it's closed under addition. And then for any real number C and any vector in U, CU is again in U. If you can show these 2, then U has to satisfy all the 8 properties that a vector space must satisfy. Now, I don't want to go into too much details, but let's just quickly go over why. Well, first, because the addition itself is from the bigger space, V, and it's already associative, commutative, it has a distributed property with the scalar, and so, and then also the scalar multiplication has the what is it? This formula, A, B, V equals to A, B, B. A compatibility condition and also the identity of 1. These are defined for the addition of scalar. That takes care of most of them. What's not clear is whether this U should have a additive identity 0. That was one of the requirements too. And also any element should have an additive inverse. those were the two more conditions that would need to be proved, and that's proved by this because, another condition is that subspaces cannot be empty. Subspace cannot be empty. Because if it's empty, then it doesn't have the zero. Okay? But as long as if it's not empty, you take any vector in U, then 0 times U will give you the 0 element. So this has to be in U if it's closed under a scalar multiplication. And for any U, -1 times U acts like the inverse, right? It is the inverse. So the inverse exists too. So just having these two properties will allow you to prove all the 8 properties that we require to be a vector space. So that's what you need to show. Okay. So what I want to say is that span is a vector space. Okay. So theorem: span of U1, U2, UN. Is a subspace. Is a subspace. Okay. So let's try to prove this. But let me just prove it. Proof for just U1, U2. Okay. Because the general proof will be the same thing, but it's like with n and all this, it's just too complicated. If I can prove it for U1, U2, then the same proof should hold for everything. All right. So let's say span. We're looking at span of U1, U2. Okay, what is this set? It's a set of anything that looks like some multiple of U1 plus another multiple of U2. Okay? That's what it is. Okay? Where A and B are real numbers. And all we need to show are two things. It's closed under addition and closed under scalar multiplication. So let's prove item number 1. If V and W, let's call this just span. Okay, so if V and W is from the span, now let's just write that. Then what does that mean? That means V is equal to, V has to look like this, right? So I'll call it A1U1 plus B1U2. W is also from the span, so W should also look like this, but it can't be this. It may be different numbers. It could be the same number, but it could be different. So I'm going to call this as what? A2U1 and B2U2. Does the naming system make sense to you? See, U1 and U2 is a fixed thing from the span. It doesn't change. But A and B are some arbitrary real numbers. So those can be anything. Okay? So I'm choosing V as, V must look like this, and W should also look like this. Okay. All right. Sorry, I should have made more space, but if that's true, what is V plus W? Well, V plus W is like this plus this and this plus this, so it's like A1 plus A2, U1, and B1 plus B2, U2. Isn't that right? This plus this is same as this plus this is same as that. But look, this is a real number. This is a real number. So this thing looks exactly like this one, where A is like A1 plus A2 and B is like B1 plus B2. So does this belong to span? Yes or no?
Yes.
Yes. Yeah. So this belongs to span of U1, U2. So part 1 is done, okay? Now part 2 is even simpler. Part 2, let me write here. Part 2, if V is in span, then V must look like something times U1 plus something times U2, right? Now let's take any constant multiple of V. What is that? That's CA U1 plus CB U2. But wait, that is again some real number times U1 plus real number times U2. So again, this is in the span. So that's the proof, but out of this very abstract proof, you just need to know the intuition. What's the intuition? If you have a bunch of vectors, right, what does the span give you? It gives you some kind of a plane or some kind of a linear space that's inside the bigger space that contains the given vectors. It's like the smallest. So another abstract way of saying it is another way to define span is this. Span U1 through UN is the smallest subspace containing U1, U2 until UN. Okay? That's what it is. Okay, now let's see if you have a good intuition of what a span is, or subspace is. Here's another question. Question. What are the subspaces of R3? Now, this notation R3 means, do you know what R3 is? Huh?
Real numbers. Three-dimensional space.
Real number with triple. What does that mean? You're collecting everything that looks like A, comma B, comma C, 3 numbers. What does that give you? 3D space. Okay, so 3D space itself is a vector space, right? So R3 is a 3-dimensional vector space. The question is, what are the subspaces of R3? Okay. So there are 3 types. Okay. Number 1, the example that we just did. What kind of subspaces are there in R3? Give me examples. We did one.
Plane?
Planes going through the origin, right? Planes through 0, 0, 0, right? What else? What if you had a span of a single vector? What would you get? What's the span of a single vector? Just U. That's some constant multiple of U, right? What does that give you? A line. It gives you a line, not a vector.
Oh.
It's a collection of vectors which gives you all the points of this line. So this is a line.
Why wouldn't it be considered a line vector?
I mean, vectors need a size, right? But this is like a collection of all the points, so it's like,
Oh, it's infinite.
yeah, it's a collection of everything. Oh, there's a slightly different viewpoint from physics definition of what a vector is and the way I'm thinking of a vector. And it is a bit confusing when you first learn it. See, physics, they call this a vector, right? I sometimes draw it just to make sense of the summation and all that, but to me, it's really this endpoint that's a vector. And that they correspond to, because my vectors always begin at 0. Okay? So the only thing I have to give you is the terminal point. If I know the terminal point, I know the vector. So, to me, when I say R3 is a vector space, elements in here are just points in space, but they're vectors too, because any point in space you connect to the origin and you get a vector. All right, so if you have something like span of U, that's like lines through 0, 0, 0. Right? So you have this 3-dimension, and you have any kind of a line going through the origin, right? And all the points in here are vectors, right? And if you just take this subset, it satisfies all the 8 conditions for a vector space, because if you have one vector and another vector here, some of those two vectors still lie in this vectors, this subspace. You can take any scalar multiple that's still in here. It's a subspace. All right. So lines through that. Now there's still another, oh, there's 3 more. Okay. R3 itself is a subspace. There's a subspace could be itself. So entire three plane, the 3-dimensional space is a subspace. Okay.
Is a point a subspace?
The origin itself, 0, 0, 0. Yeah. Subspace. As a set. So the set that just has a 0 vector is a vector space almost trivially, because if you check all the 8 conditions, 0 plus 0 is same as 0 plus 0. You can see commutativity, associativity, all the conditions, they are satisfied trivially if you just have this. Okay, so that's it. Yeah. Those are the subspaces of R3. Now, to have a better idea of what subspaces are, then we can't just stop here. We have to go to the 4th dimension. Oof, right? Okay. So, what is a 4th dimension? Yeah?
I always perceived it as time.
Okay, you can say that.
Mathematicians don't like hearing that, I guess.
No. Actually, that's a very good way to think of it. You can think of the 4th direction as the time, and it actually, I mean, the way you think of, you understand the world is it's really a 4-dimensional space where one of the directions is the time. And Einstein was the first to realize that there is no natural dimension, natural direction of time. Like, depending on how you move, the time axis could be tilted.
Time is relative.
It's relative, yeah, relatively. But anyways, very abstractly, this is the 4th dimension. Okay? What's a 4th dimension world? It's just 4 numbers. That's dimension 4. Okay? Now, what are the subspace of this? Well, it's a 3-space. 3 planes. So subspaces of this would be like 3 planes. So we call that 3 planes, but what I really mean is that it's like a linear flat space that's 3-dimensional, right? And it could also be it could also be 2 planes and lines and this single point and R4 itself, right? All of these have to go through the origin. 0, 0, 0.